So pneumatic, ECS, and pressurization. And the reason I combine these and then kind of the next section, which includes like oxygen, is that these build on each other. Turn our attention up here. Okay, so the pneumatic system is our bleed air supply. You'll often hear it referred to as bleed air. ECS is the acronym for environmental control systems. Okay, we don't really use the term heat or air conditioner. We don't have heaters or air conditioners on the aircraft. We have hot air from the bleed system, and we have air cycle machines, also known as packs. And then pressurization is, we want to make sure that people don't pass out when we fly really high. So these are generally covered on the airframe side in ATA 21 and 36. So pneumatic and bleed air is covered in 36. It also has a section 75. What's 75? That's the engine bleed air portion of it, right? So any of those 70s, any of those ATA codes that fall in the 70s typically have to do with engines. So bleed air pneumatic is kind of going to be covered in both. Most of what we're talking about is going to be in 36, but there is some stuff I'll mention that comes out of 75. And then environmental control system is ATA 21. And that's going to have our heating and air conditioning, but we don't refer to them as heaters and air conditioners. And then pressurization also falls under ATA 21. So often, if we put these all together, they're referred to as the air management system. And you'll hear that as a term in the industry. So looking at the aircraft and the air management system, you'll see things that look like this. So this shows the duct work coming off. We have our engines, and our engines are going to be our supply. Various ducts going everywhere. We're going to make hot air. We're going to make cold air. This duct, what's this duct coming from the tail right here? That's the APU, right? So the APU is another bleed air source. And then it's going to provide, we have the air conditioning packs, airfoil, anti-ice, de-ice, we have to ventilate our avionics, right? They get hot. Pneumatic bleed system, and then things like water tanks, water and waste also runs off of this. If you've ever been on an airplane, flush the toilet, you hear the vacuum system, right? And it works even on the ground. In flight, you can use some pressurization things going on there to help with that, but on the ground, you have to provide some kind of a vacuum source. So pressurization also can be used to create a vacuum. And then all of that, we want to make sure that if we have a problem with the system, that it doesn't get too hot, or that we don't have hot bleed air leaking into the wrong spot where it can cause damage. And it can cause damage. We had a cleaner one time put one of our airplanes, you can run these in auto or manual. Manual gets rid of pretty much any of your overheat and underheat under temperature protections. They put it in manual and cranked it all the way to hot. The plane was sitting outside running on the APU. And about an hour later, a different cleaner came into the hangar, and so, this was in Salt Lake City in the winter. Different cleaner came into the hangar and said, hey, this guy was messing with something in the cockpit, and it's really hot, and the plane smells like burning. And we were like, okay, what's going on there? So we go out there, we realize that the heating system was set to full hot, and it actually got so hot that most of this duct work, not the bleed air supply, but once you get into like the temperature in the cabin and the avionics cooling, it's all fiberglass ductwork. It got so hot it delaminated all the fiberglass ductwork. And so that was tear the entire interior of the plane out to replace all the fiberglass ductwork that had been overheated. So yeah, it's an expensive job, and the bigger expense is that the plane was down for a period of time. Really, the biggest expense on a lot of these aircraft is downtime if they're in a commercial environment. So, yep. So for someone that shouldn't have been even touching whatever, didn't understand how it worked and shouldn't have been doing. Yes. The flip side to that too is if you put it on full cold, it'll actually ice everything up and it'll damage items too. They can get so cold that they can freeze. And so they actually can blow like snow. You'll get ice chunks coming out of the vents if you set them too cold. And that means that the turbines in there are icing up, which throws them out of balance, and then they chew themselves up. So the division point between these is typically near the engine, we're going to have a shutoff valve of some kind. And it's either right at the shutoff valve or just downstream of the shutoff valve somewhere. Like here, it's showing this division point is kind of in the pylon area. So in kind of gold, yellow, whatever color that is, That is your ATA 75 engine pneumatic system, and then everything in gray here is the airframe bleed air system. And so pylon firewall shutoff valve is often somewhere in the pylon or in where the engine's mounted. And we have this valve. The biggest reason is in fuel, we looked at one of the things you had to figure out is that in a fuel system, there has to be what you have a fire zone. You have to be able to isolate an area that's prone to potential fire, i.e. an engine enclosure. And part of that is you need to shut off the flow of air because you don't want, say, smoke making its way from that area into the rest of the aircraft. And for control. If we look at it in a schematic form, this is, here's kind of the schematic. The areas here that are within the boxes, the left and right engine in the boxes, that is your ATA 75. And then the areas that are kind of outside, again, is just showing the airframe bleed air portion of it. And you can see sometimes there's shutoff valves in different spots. But again, that division point is typically, this is your pylon area. So in this case, the engine is in here to the left of this firewall line. Here's that kind of main shutoff valve, this NAPRSOV. So it's, let me think. I know the PRSOV is pressure regulating shutoff valve. I can't remember what the NA stands for on this particular aircraft. But you'll often see PRSOV as a common acronym, pressure regulating, so it sets the downstream pressure, and then it also serves as our on-off valve, our shutoff valve. So it kind of has a dual function there. Again, can't remember what the NAP, like right here, you can see there's an HPSOV, that one's an either on or off valve, it doesn't regulate. So one sets the pressure downstream in the rest of the aircraft. The other one is for turning things on and off. And then you can see here, there's like what's called the pre-cooler here. This is in the pylon area. So the pre-cooler is often in the pylon, or it's in an area where most likely it's going to have fan bypass air that's cooling the pre-cooler. It's kind of like a radiator to help cool the air, because the air coming off these engines can be 300, 400, 500, 600 degrees. We don't need anything that hot going up to the airplane. And so we pre-cool it before we send it up to the rest of the airplane. Okay. If we look at it from a ICAST or indication and control standpoint, we get a schematic that looks similar. So here you can see our engines, the shutoff valve. A lot of this stuff that's shown in the engine isn't shown on the ICAST schematic. We can either show that it's on or, okay. What we do see is a little bit more of the airframe side of things. So we can see our flow control valves going to our air conditioning, heating and environmental control system packs. So those are, I think, standing way too close. Those are going to be downstream of these points here. You have your wing anti-ice shutoff valves, which aren't actually shown on here. There's a separate page for the anti-ice system. Okay. And then you've got your cross bleed. Normally you isolate the left and right side, but you connect them together to run everything off the left or off the right or off the APU if you're down to a single source. You can see we have an APU connection right here, as well as a high pressure ground connection. Okay. So here's our little APU shown here. Now what it doesn't show here, there's no ground connection shown. That appears when you actually have pressure, when you're connected and have a ground card hooked up. Okay. And then the controls here, pack controls, bleed valve controls, and then temperature selection. And a lot of these nowadays are pretty much run in auto. They have an auto that runs most of the time, and then when it, if you need to do something reversionary for testing or in a non-normal situation, then you have the ability to either force things on or off. So I'm gonna just pause for a second here. So pneumatic is our bleed air source is gonna be used by quite a few different things, but some examples. So I mentioned we're gonna be talking in detail about ECS, environmental control system, cabin heat and cool, and then pressurization. Other areas where pneumatic bleed air is used, it's used primarily engine starting, any kind of regional jet and above size-wise, or larger corporate jets, they're going to use bleed air for engine starting rather than electric starters. Some aircraft, the thrust reversers are driven pneumatically. Others, they may be hydraulically driven, but a lot are pneumatically driven. Anti-ice for things like our wings, tail, cowling, sometimes some other areas, but those are the three primary areas that get anti-ice using bleed air. There are other types of anti-ice. There's electric anti-ice as well. That's often used for things like pitot tubes and windshields and stuff like that. But for wings, tail, and cowl, most of the time, and I put an asterisk there except for the 787, most of the time, pretty much everything but the 787 uses bleed air. 787 is actually electric. They went back to they have an electric architecture. Hydraulics, when we did hydraulics, we talked about having things like pressurized reservoirs, right? Pneumatically pressurized reservoirs, as well as you can have an air turbine that can drive a hydraulic pump. So this would be the source for that. Fuel system, there are cases where bleed air can be used to provide head pressure in addition to the vent system. I have thrust reversers on there twice. I think I noticed that last year. I keep forgetting to take that off. Potable water and vacuum waste. I'll kind of put potable water and waste go together. So on a lot of aircraft, rather than using pumps to force water up to the coffee makers and up to the spouts and the sinks and that kind of thing, they'll put air they'll pressurize the water tanks with air, and that will push water out when a spigot is opened or whatever. And then the vacuum waste part of that, put it using a venturi to create a vacuum and having the suction toilets and those kind of things, particularly on larger aircraft. Most of your smaller regional jets use more of a chemical toilet, something very similar to an electric motor that kind of circulates water, but vacuum waste systems are used on most of your larger aircraft. So our primary source in flight is going to be our engines. We're going to generate it we are going to pull bleed air from the compressor. That's a key point that a lot of people kind of seem to forget. People are like, well, how can we use pneumatic, this bleed air in order to pressurize the cabin, because we're going to kill everybody with carbon monoxide poisoning, right? Because they're saying, oh, it's coming off the engine. Well, remember, the compressor, you have your inlet, your compressor, and then the combustion chamber, and then the turbine. The air is moving from one end to the other, right? You have a turbine engine has your 4 stages occurring simultaneously in 4 different locations, right? Inlet, compress, combust, or turbine and exhaust, right? Whereas your piston engine has 4 different functions occurring over time in the same location. So our bleed air connection is hooked to the compressor, which is ahead of the combustion chamber. So at that point, the only thing that should be in there, should be is a big thing, but the only thing that should be in there is compressed air that's pulled in from the outside. Okay. 737 MAX, it's in the news again. They have an issue right now where it's getting, if they have to do, I'm trying to remember exact scenario on takeoff, if they have to shut down an engine, there's a system that decouples the fan and it actually blows a ton of oil into the bleed air. And so there's been 2 incidents that I know of where they've sent a ton of oil vapor, hot, and remember, it's hot, so it's not just oil vapor, it's burned oil vapor, which can be very nasty, and into the cabin. And one of them, what they're afraid of is if one engine primarily sends it to the cockpit, if it does the cockpit, it can actually fog the cockpit out so bad that you can't see anything. So there's a investigation into that right now, what's causing that. Well, it can be, you can solve it operationally by, if you have to shut that engine down, you shut off the pack that's connected to that engine. No, it's a procedural issue and engine problem, and there's a whole bunch of factors that go into it. The APU is our secondary source, okay? And it can also be used, our APU is primarily used on the ground, okay? And then ground air start carts, huffer carts, or something called a bottle cart. Basically, a ground air start cart or a huffer cart is basically like an APU that's on a little cart that you can tow around with a tug. And it's got a hose that you hook up, and that's what that external air connection is. A bottle cart is just it's a giant tank that is pressurized. It's pre-pressurized, and that's got a valve with a hose coming off of it. And you can use it to start engines if you don't have an APU available. The thing with these bottle carts is oftentimes they just use a small compressor to pressurize them. And so we had one at the first airport I worked at was a small airport. If we had to use the bottle cart, you got 2 start attempts before that bottle was empty. And if you didn't get it right, it took about 6 to 8 hours to repressurize the bottle because all it had was like a little shop air compressor trying to fill this giant air tank. And so every once in a while, if a plane was deferred, a pilot wouldn't get the engine started properly, and the plane would be stuck for the next 6 hours until that cart got going again. Okay. Bleed air, though, is expensive. We have to keep that in mind. So bleed air, on bleed air, you're going to take air off the engine. And so the engine has to work harder to make up for that. And so what that results in is higher fuel use. It can result in reduced thrust. So oftentimes during takeoff, the amount of bleed air being bled off will either be shut off or it'll be reduced. Okay? Anytime you increase fuel use or decrease the amount of air going through the engine, you're going to get an increase in heat. So the engine's going to run hotter, and an engine running hotter is going to be subject to more wear and tear. Right? So it is expensive, and that's why, like the 787, when I say it's gone to a no bleed architecture, Boeing found it was more efficient to put 2 generators on each engine instead of 1, 2 large generators on each engine instead of 1, and then run everything electronically from there. So their anti-ice is electric. The pressurization and environmental control, they still use bleed air, or they still use compressed air, excuse me, but it's a compressor that runs off electricity that compresses outside air and sends it into the ECS and pressurization system. So, you know, there may be some more aircraft down the road. As far as I know, the A350 is still bleed air. The A220 is still bleed air. You know, I'm thinking of all like kind of the newest passenger aircraft. Yeah, the 37 MAX is an old airplane with just some fancy displays in it. But the architecture, the airframe architecture, the systems on it are shared designs going back to the 1960s and 70s. Yeah. That's what Boeing figured. That's what they decided, and that's why they went to big generators and no bleed air. So, maybe. Oh, you have plenty of redundancy here, though. So pneumatic bleed air control, we're going to have a few ways we have to be able to control our bleed air. The first one is be able to turn it off and on. So we have something referred to as just a shut-off valve, or the common, as you saw in that diagram, the acronym SOV is the most common acronym you'll need for a shut-off valve. So these can be run a couple different ways. They're almost always electrically controlled. If they are able to be controlled directly, they're going to be electrically controlled. But that electrical control can operate them a couple different ways. One is they can be pneumatically operated. So where they actually pull a little bit of bleed air into a diaphragm, and there's the electrical control controls air being routed to a diaphragm, and that pushes the valve open and closed. The other way to do it is just run the electricity directly to a motor, and the motor is going to open and close the valve. So if you have these, one thing to remember when you're maintaining the aircraft is what do you have to know if you're trying to troubleshoot one of these first ones? What's an important point? What's that? The way it's operated. What do you have to operate it? You have to have air pressure. You have to have your pneumatic system pressurized. If you are just trying to like see if the valve will move, it will not move unless you have air pressure. Whereas something that's motor driven, a lot of times you can open and close it, and you can operate it without having pneumatic pressure available. So every once in a while we would have a pilot that maybe had flown a different aircraft or had a brain fart, or we had a couple different types of aircraft, and sometimes things work differently. They would like try to test the valve, and they'd be like, well, the pack shutoff valve won't work. Air conditioning shutoff valve won't work. Like, no, it doesn't. It won't work unless you have your pneumatic system on, unless the APU is running, the engines are running, and you have bleed air available. So we'd get a write-up like that, and we'd troubleshoot it. We'd troubleshoot it. Minimal troubleshooting was verify. First step in troubleshooting, verify the fault. And we'd say, well, this one is pneumatically operated. You got to have pressure available to do it. Even mechanics would sometimes do that. Someone would, not think about it.
Switch on it.
Could, or not getting air. If you need to have if you're running the APU, you got to have the cross bleed valve open. The left side's working fine, but the right side's not working because you forgot to open the cross bleed to send pressure to the right side, right? Check valves, spring-loaded close, pneumatically open, just like any other check valve you've seen. Check valves typically don't have any type of indication on the outside. They typically don't, there's no control. There's no wires going to them most of the time. I can't think of a check valve, particularly a pneumatic check valve I've ever seen that had any kind of wiring going to it. And so, those are just to prevent air from going backwards. And there were a couple check valves that we'll see. Load control or pressure regulating valves. So these are going to be similar to your shutoff valves, but instead of being fully open or fully closed, they now have the ability to modulate or to open a small amount or open a large amount, depending on what we want to do. And what that can be done, it can do a couple things. Like on the engine, right, the bleed, is we can vary the load placed on the pressure source, right? So like I said, during takeoff, those load control valves, the shut-off load control valve may partially close. It'll reduce the amount of air available to run the environmental control system, but it will prevent the engine from bleeding off so much air that it could overtemp. The flip side to that is your pressure regulating valves, and that is downstream. Once the engine, once you're up running, full pressure coming off the engine, the engine may be able to put out 60 or 70 or 80 or 100 psi, but the rest of the aircraft, the airframe bleed system, is only designed to run at 45 psi. And so you'll have a pressure regulating shutoff valve that will modulate the amount of airflow going into the pneumatic system as a whole to maintain a proper pressure. When you turn something on, you turn on a pack, all of a sudden there's more demand, that valve will open more to keep that pressure. You shut the pack off, there's less demand. Pack is a air conditioning pack, by the way. I think I said that earlier, but just to make sure. You shut the pack off, there's less demand on the system, so that pressure regulating valve is going to scale back the amount of air going down so that the pressure doesn't get too high. And again, these can be torque motor controlled, is pretty much the same as the solenoid, except now it has the ability to vary the position. And then motor driven, again, just a little electric motor that can drive the valve open or closed. And I'm doing this because most of these are like butterfly valves. They're a butterfly type valve. And then the last one's a combo valve. A lot of these aren't the same thing. So a lot of times your shutoff valve, your load control or pressure regulating valves, they're the same valve. They can be driven to a fully closed position for shutoff, or they can be in some other. So that's where you get your pressure regulating shutoff valve. That's where you get your load control shutoff valve, or load control shutoff valve, or load control, what's LCSO? I think it's just load control shutoff. I don't remember what that full acronym was, but and they make all kinds of other names. As you saw, here they've got NAPRSOV, and I can't remember what the NA was. Been too long. So high pressure shutoff valve here. So that's just a shutoff valve. Here's a shutoff valve going to wing anti-ice because the pressure's already regulated after this here. So the shutoff valve going to wing anti-ice is just an on or off. The valve going to the packs is going to be a regulating valve. Starter, valve going to the starter is a shutoff valve because we're just going to send air to the starter. Anyone know what NAIV is? Naive. It's naive. So that's the nacelle anti-ice valve. So it's going to the cowl anti-ice. They call it the nacelle anti-ice. Okay. Anyways, go back. So what do these look like? Here is a kind of an example of a valve, and this is showing one of those, one of the ones that is pneumatically operated. So you can see we've got air coming in here. You can see some of the air is able to go up, right? And it goes to, this is a little actuator right here, okay? And that actuator, when it moves left, right, it's gonna open, this is a butterfly valve in the middle right here, okay? And so what it's doing, where these lines are going, they're going to something called a torque motor. And a torque motor looks like this. And so the torque motor it's taking pressure and it can route it to either side of this little actuator to vary the position of the valve. So kind of showing the details. I'm going to go to this page because here I show how it's kind of hooked up. So here is our full pressure. It goes through a little filter, so if there's any oil in the air or whatever, it doesn't gum up the torque motor. Okay, that provides air pressure that then the torque motor here is going to vary. It's got a little, this is like a little solenoid operated kind of wobbly thing. And then here is the actual valve itself, so it can move this little solenoid here, can rock this T back and forth, and that can route air out in order to control the amount of pressure on the opposite side of the valve and to vary the position. So you can either route, if this is closed like it's shown here, pressure, there's a lot of pressure here on the left side, the closed side, but there's really not much pressure going here to the right side, right? If this little tab inside the torque motor swings to the right, then air is going to be, it'll shut off the kind of the bypass. This duct here on the right goes to ambient pressure, just sends it out to the air. And then it swings to the right, closes that off, and it sends pressure over to this side. And because you've got a larger surface area on the right, that's going to push this whole piston to the left, and it's going to cause the valve position to change. And so it can vary it based on how that little tab moves back and forth inside the torque motor. It can vary kind of that pressure differential in order to do any position of this regulating valve. Okay. And some of these too, in addition to having pressure, checking the upstream pressure, they'll also have a port on the downstream side so that they can use that for pressure regulation as well. Okay. So, yep, there's my little actuator. Going to move left and right, as I mentioned, and port the amount of air on each side of the actuator. Okay. Throughout our system, we're going to want to make sure, I mentioned earlier, we're going to have some kind of a leak detection system. So bleed air can be very hot, particularly near the engine, right, coming on into the nacelle area, and even somewhat close to the engine. So we don't necessarily have leak detection over the entire length of the system. It's particularly in those areas where the temperature is high enough where it could cause damage. And so these are going to be very similar to what you've seen with other fire detection systems. So it's going to be those Kitty or Fenwal style loops is one version. There's kind of two versions, looped or spot detectors. But the looped elements are essentially the same as the Kitty or Fenwal loops that you've seen those in another class, right? Did Jeremy talk about them at all? Oh boy, that's right. Things changed when he used to. He doesn't anymore. Okay. No, it's how we divided up content that changed. Okay, so these are looped elements. What they are is they are metallic, little tiny metallic tubes. We're talking like 1/16 of an inch diameter. And you'll see them running alongside ducts, or you'll see them around engines and that kind of thing. And there are two types. The reason I say there are two types is we have one type was originally made by, so Kitty and Fenwal are two companies that make fire or fire protection devices, detection and protection devices. And originally Kitty made one style and Fenwal made the other. The fun part today is that the patents have expired on both of those. And so Kitty makes both Kitty and Fenwal style, and Fenwal makes both Kitty and Fenwal style loops. But we still refer to them by the original name. So they look like, again, they look like a little tube that is run alongside things. But if you cut them open, so if we cut them open, and I'm going to put style because remember, they can both make either one nowadays. So Kitty style or Fenwal style. Inside of these loops inside of these tubes, there is going to be kind of a center conductor. And in a Fenwell style, there's a single center conductor. Okay? In a Kitty style, there are two conductors. Okay? So how do you think you can remember the difference between them? Pig nose. Let me rewrite Kitty here. So this is how I remember when I was trying to remember it. So I always remembered it because the two D's kind of looked like the two conductors, right? Okay, so there are these loops running inside, or these conductors running inside, and then surrounding them, this area is something called eutectic salt. What's that? Eutectic salt. T-E-C-T-I-C, eutectic. There we go. Yeah. I hope you know how to spell salt. Okay. And what that does, what that eutectic salt does is when it reaches a given temperature, and they can make it, and someone asked us, what is it? I don't know what the compound is. And they make different compounds because these are calibrated for different temperatures. So they can be used for fire protection. Those ones are going to be triggered at a high temperature. They can be used for bleed air leak detection. Those will have to trigger at a lower temperature. So that what determines whether it triggers is what the compound, what that eutectic salt compound is, and what temperature. Essentially what happens is it starts to kind of melt in a way, and when it does, it becomes conductive. So normally when it's solid at room temperature or cooler temperatures, it's an insulator. And as it heats up, it begins to conduct electricity or allow conduction. Now, it's not like an on or off. It's not a true switch. It becomes less resistive, right? And so there's a point where it'll conduct enough electricity that when we hook these test loops up to the controller or the computer, right, what'll happen is on this one, this outer shell is connected to a ground somewhere, usually right at the end of it. On this one of the loops is connected to a ground, okay? The other end, the other conductor, or the central conductor, this goes to our fire or overheat controller or computer. Here. Fire or, depending on, again, if it's a fire loop or a overheat loop, okay? And so what's happening is that fire and overheat controller is looking for a ground on here. So under normal conditions, it should not see a ground, right? Because that center conductor, or the conductor here, the right-hand conductor in my example, is connected to it, but then it's insulated from a ground by the eutectic salt. But as the temperature rises and it gets to a certain level, can everyone see that okay? Does it show up? Does that help or hurt? Well, does it help to see this? Okay, so as the temperature goes up, makes that harder to see, but as the temperature goes up, that salt, the resistance drops, and at a certain point, then this wire or this conductor that the fire and overheat controller is connected to will be able to sense that ground. It'll see that ground. There'll be continuity to ground. And that gives an indication of a fire or an overheat. Okay? And they're more sophisticated now where they can actually see like rate of rise, how quickly it can see how quickly the conductivity is increasing. It can see what level the conductivity is at. And so they've added more logic to them now where to prevent like false alarms and that kind of things. Because what'll happen, like if you pinch one of these, you instantly get a hard ground. Well, if the computer sees an instant hard ground, it doesn't automatically send out a warning. because it's like, wait a minute, a fire or an overheat can't do that. A fire and overheat is going to cause that conductivity to increase over time. And so if it sees like an instant one, it knows something went wrong, like a loop got pinched or broken. These are real fragile. If they get kinked or bent, when you wind them up, they come in like a reel, and usually you don't want to wind them much more than about 1.5 feet in diameter, because if they get a kink in them, it'll crunch the tube and it'll cause a short in them. Okay. Also, if they get overheated, when we do one of these, you're going to do one of these in lab. If you put the you get too aggressive with the blowtorch we use on them, it'll cook the loop and it'll permanently damage the eutectic salt. So it does. When it cools down, then it goes back to being an insulator again. No, the kink causes the metal shield to crunch against it, or it causes these two to get, these are very, remember, they're like 1/16 of an inch diameter. They're very, very small. So just a little kink in there crushes the whole, it gets crushed essentially. Or if they get worn through, I've seen them get chafed before where they're rubbing against something and then they ground out. Or we had a whole like problem was our wing leading edge overheat detector and loops. They would get a little bit of corrosion in the connectors. And we had all kinds, we were constantly fighting these things and we were trying different things to get them to work right. It was a nightmare. The other thing that can happen is there are certain ways to test them. Sometimes you can put a meter from like one end to the other to check for continuity or check that. Well, even a multimeter, if you put on some of the loops, if you put a multimeter on here and here, it has a high enough voltage that it'll actually zap through and it'll damage the loop by putting a multimeter on it. There was a special test meter you had to use that was a very low voltage so that you wouldn't zap the eutectic salt. So just when you're working with these, you got to know they're fragile. They're somewhat fragile, okay? Yeah, exactly. Okay. So now that we've got that part, which is what Jeremy used to cover, so these loops would be run alongside. And here's a kind of an image of the loops. So here's our ductwork, right? And then you can see this little black kind of chain, and it looks kind of like a ladder. And the reason for that is most of the time these loops are run in parallel. There's two loops run side by side. And that does two things for you. One is it increases redundancy because we have the ability, they're usually referred to as loop A and loop B. We have the ability, if we need to, if one of the loops goes bad, we can tell the computer or we can flip a switch that says just look at loop A or just look at loop B. What's the advantage of looking at both of them most of the time under normal operation? You could well, that you can figure out flipping, but they're going to prevent something. What are they going to prevent? It's going to help prevent false alarms. Okay, especially when they're fire loops. You really, really don't want a false alarm with a fire loop. Okay, so for redundancy, you can shut one off or the other, but most of the time you're going to look at both because you want it. You need a situation where both of them are indicating before it gives you a caution or a warning. Okay, and so they are. They're typically run side by side along the sides of the ducts. Now, one of the things we do is if you're running these along one side of a duct, the issue can be that the leak is on the opposite side. So you get a crack in a piece of ductwork. And say the loop's running along the top and the crack is on the bottom. Will the loop be able to sense it? Should be shaking your head no, because the air is going to be blowing down and the loop's going to be up here somewhere. Right? And so what we do is in these particularly areas, we'll oftentimes have what's called a double layer duct. This is terrible to erase. So in an area where we have these, we'll have double layer ducting. And this applies for both when we get the spot detectors as well. So if we have a duct, so here is our duct. That's a terrible marker. Here is our duct. Okay, we have a duct running through, right? And this is a cross section. We're looking at the side of it. Okay, great duct. Okay. There will be a second duct, what's called a coaxial duct, around the outside of it. Think of it as a tube within a tube. Okay. tubed within a tube. And then say our loops are run up here, right? So if this was a single layer tube and we got a crack down here, right, the air would blow away from the loop and we would never sense it. So the way these are designed is this outer tube, oops, don't do that. This outer tube actually has holes in it intentionally. Something like that. And so now if I get a leak down here in the bottom, my air will go into the outer tube and it'll be directed up, it'll be directed out the holes that point towards our overheat loop or our fire loop. In this case, this is for overheat. Okay? So that outer tube, all it is there is if the inner tube gets cracked, the actual duct gets cracked, is to route that leaking air towards the loops that are going to sense it. Same thing can happen with spot detectors. Spot detectors, bimetallic strips. If I say bimetallic strip, anyone know what I'm talking about? Probably not? Okay. So this is the other technology we have is a bimetallic strip is if you have two pieces of dissimilar metal that are bonded together that have different coefficients of expansion or contraction. What's going to happen when I heat this? It's going to bend, right? One of these is going to expand faster than the other, and it's going to cause this thing to bend. And so what I can do is I can hook a wire to this end, right? And I can put a little switch contact on that end, right? And so when this heats up and it bends, it's going to cause it to bend, and it's going to, in this case, have it either disconnect or connect a switch, just depends on the design, either bend or straighten. It's going to bend, and it's going to disconnect that switch. Okay? So that's what a spot detector uses. Okay? And again, these can be in a couple different places. One of them is, instead of a loop, you put a spot detector near each of these holes, right? And these spot detectors are connected in parallel. They're basically like a bunch of parallel switches. Actually, with opening, they would have to be in series. So if they're opening, they have to be in series. If they are closing, they would be in parallel. But it will cause, when heat hits the switch, it'll do the bimetallic strip, whether it's opening or closing, and it'll send a signal that there's air leaking and trigger that. And most of these nowadays, if there is a duct that gets an overheat, it will cause the shutoff valve to automatically close. The pilot back in the day, you'd get the light, the caution, crew would have to shut the valve off. Nowadays, everything's, all the computers are talking to each other and the valve automatically closes. That's that auto mode. And so the other spot these can be is if you have joints in ductwork. If you have two places, the most common location where you get a leak is where you have two ducts that come together and have a clamp. They use a V-band clamp to hold them together. Is if that starts to leak, oftentimes you have spot detectors in those areas. Okay? And that's going to feed into your monitoring system computer in order to tell you if you have an overheat. Okay? So we are going to leave off there.